Okay, so let's talk a little bit about this lesson. So, one of the main things about this lesson, we're going to go over pretty much the same properties. It's just that when we're talking about, when we're trying to prove things, we want it to be more specific. We need to be able to explain ourselves. So, there's a couple of different things that we can use. When we're talking about proofs, we use a few different things. So one of the things is to make sure that we understand the difference between proofs and theorems. Theorems are often things that we use in proofs. So once we have proven one thing, once we have proven a theorem, we get to use that theorem for future proofs. Now this is kind of cool because it's like a video game. Have you ever played a video game to where usually role-playing games or puzzle games, some roguelikes and stuff like that, to where you want to get to one area or unlock something, but you need to go and do something completely different. So like they're kind of the Metroidvania type games to where you have to have the missiles to be able to open certain doors or something like that. Basically, you're trying to get something to unlock something else so that you can get something to unlock something else, etc. Geometry is a lot like that, and a lot of math and proofs, they're a lot like that as well. So basically, when we look at this, we have this long definition for a proof of a mathematical statement is a detailed explanation of how that statement follows logically from other statements already accepted as true. So if we know a bunch of true statements, then we know for a fact that they're true, either from axioms, which are things that are given, like things that are always true, that it's pretty easy to look at and go like, that's definitely true, or theorems. And so we use these true statements, these things that we have proven to be true and we know to be true, to prove other things. So, and often we use theorems. We use theorems for this. And a theorem is a mathematical statement with a proof. So once we have proven something, it is a theorem. It is a statement that has been proven, so it is a theorem. And it's usually an if-then. It's like a hypothesis at first, and then we prove it. It's effectively like a fact. And like this says, it's like once a theorem has been proved, it can be added to our list of known facts and used in future proofs. So it's like we unlock different things. So in this case right here, we're looking at the diagram to the right. If you're given that these two lines, A, B, and C, D, are parallel, so that's a given statement. It's kind of like in this case, we have defined that they are parallel, or in real life, we've noticed that they're parallel. And we might have proven that they're parallel. Who knows? How can you use your knowledge of how vertical angles and alternate interior angles are equal in measure to prove that x equals w? So we're given that AB is parallel to CD. So often when we're given something, we like to write that down. AB and CD are parallel because someone else might not have that information. They just look at it and they don't know. Notice there's no symbols on that little figure. So we'd often write down the statement that we're given and just say, hey, that was given. They told us that. They told us that that's true, or we noticed that it's true in real life. So we're trying to prove that x equals w. And they've told us that the things that we can use are vertical angles. So like these things are vertical angles. And alternate interior angles. So these are alternate interior angles. And our goal is to get this equals this to prove corresponding angles. So in this case, we haven't proven corresponding angles, so we can't use it. We can't use what we're trying to prove itself. It's circular, and circular logic is not, is kind of like a fallacy. So when we're looking at this thing, we can use vertical angles. So I look at this and I'm like, okay, well, first thing to have, vertical angles, that's cool. So I can say, maybe I start off with alternate interior angles are equal. Maybe I start off with vertical angles right here. Whatever I do, I need to get x and w equal. So I'm probably going to have to go a few little different steps for this. So they said I can use vertical angles. So let's look at it. Let's say, all right, well, W and Z are equal. So W equals Z, and we'd write down because they're vertical angles. And we'd write out all the words, like we might say that vertical angles are congruents, etc. So W equals Z. Now, we need to figure out a way to relate W to X or Z to X. One of those will get me. So the other thing that they say is that I can use alternate interior angles. Well, these are alternate interior angles, so I have a statement that says X equals Z because they're alternate interior angles. And I'd want to write out all the words. A lot of the leap ends up being like fill in the blank proofs, so it's really important that you understand your properties and that you can kind of analyze what they've written and kind of know where they're going with it so you can fill it in. So I have these two statements. I have W is equal to Z because they're vertical angles, and I have X is equal to Z because they're alternate interior angles. So we're allowed to do that. But what's cool about this is that when W equals Z and Z equals X, we can use either the transitive property or the substitution property of equality, either one works, to set them equal. So they're both equal to Z, so I can replace this Z with what Z is equal to, that X right there if I want. So I can say that W equals X, and I can say that it's because of the transitive property. Or I can say substitution property. Both of them would get me there. Transitive would be if A equals B and B equals C, then A equals C. And that's the same in this case. If W equals Z and Z equals X, then W must equal X. And you can look at it in the reverse too of X equals W. They're both the same thing. So now that we have these facts available, we've unlocked corresponding angles because we just proved corresponding angles. This is a corresponding angle with this. So we've proven that, so we've unlocked corresponding angles. So using any and all of these facts to prove that interior angles of the same side of the transversal are supplementary. So if we're trying to figure out two angles right here like that, and say that they add up to be 180, then maybe we label it, maybe we don't. I kind of want to get y'all used to this notation because, of course, you can go to each one of those angles and label it with a letter. All of that works. But just writing measure of the angle BGH also works because we need to be able to read those types of things. So you start off right here, and you go BGH. So the center thing is the angle you're talking about. So the angle formed from those 3 points is going to be that. So we're given that A, B, and CD are parallel, and that we have a transversal EF right here. So we want to prove that the measure of this angle, BGH, is plus the measure of this angle are equal to 180 degrees. All right, well, let's look at that. Let's say, well, maybe we write down that we don't want to shift our cases. AB is parallel to CD because that's given, kind of write it down as if someone's reading this, but not the requirement. And then we say the measure of angle BGH. How can we relate that to something? Well, this angle right here and this angle right here, well, those are a linear pair. We do have that information. That's in our list of stuff. Let's look at that part. Yeah. So that's something that we know that we kind of proved in previous years, and we've proved a couple times in this year. But basically, when you have 2 angles on a line, the amount of angle you have to go through to get from one side, from a point on this line to a point on this line, is 180 degrees always. So when we're doing this right here is a linear pair, so they add up to be 180. So we can say that the measure of angle, what is that, BGH, is equal to the measure of angle, what is that, AGH? AGH, not equal, plus equals 180 degrees because it's a linear pair. And we'd write that down, linear pair. Okay, and then we have, what else do we know? Well, we know that these two add up to be 180, and so, what else can we do? Well, let's kind of try to relate something with this. Well, if you look at this, I'm going to kind of use a different color and highlight this and this. Those are alternate interior angles, and we know for a fact we can use that. So we can say that the measure of angle, what is that, DHG, is equal to the measure of angle AGH because they're alternate interior angles. So that's given us a relationship between this thing that adds up to, both of those that add up to be 180 degrees and this part of it. Because we want to prove that this is equal to that. So if we've done that, we can just use substitution. Like notice I'm looking to prove BGH, which is this. So the measure of angle BGH plus the measure of angle DHG. So what's cool about that, though, is that I have this statement, measure of angle BGH plus the measure of angle AGH. But here's what's cool about that. I have this statement right here that says that's equal to DHG, which means that I can use substitution right here. And instead of writing this part of that first equation, I can write what it's equal to using substitution. The measure of angle BGH. And that's equal to 180. And that's because of the substitution property of equality. So again, the way I did that is I set up this equation because these are linear pairs. We know that. That's one of the things that we can use. And we know that we can use alternate interior angles to say that these two are equal. That way we can replace this part that we don't need for our proof with something that actually relates it to something that we do need for our proof. So instead of writing measure of angle AGH, we'll write measure of angle BGH, DGH. I wrote it wrong. Wrote the whole thing wrong. Keep saying it wrong. This side, this thing. Whatever I've shown that was equal to it. So that's what I wanted in there. This allowed me to replace the measure of angle AGH with the measure of angle DHG. And then once I replaced it in that equation, I had the exact equation that I was trying to prove. So we proved that this plus this was equal to 180 degrees. And we used a linear pair. We used alternate interior angles, and we used the substitution property. So again, now that we've proven this, we can use this to our available facts. So it's like our toolbox, it's like our inventory in a video game of key items that allows us to unlock future stuff that we can use. And our final boss is the loop test. Not a very good example, but, I like it. So in this case, now that we've done that, we can use interior angles on the same side of the transversal add up to be 180 degrees. So use any of these four facts to prove that three angles of a triangle sum to be 180 degrees. Well, that's not too bad. Now, regardless of what we do, we can always make an auxiliary line. So wait, most of our stuff has dealt with transversals, so most of our facts deal with that. So let's make a little auxiliary line just to make that we're going to say is parallel to this. We're inventing it. We are constructing it by saying that by construction, by how I did it, no matter what I have to do to get it, maybe it's, sticks on the ground, I guarantee with a level or something like that, that they are parallel. Doesn't really matter. We have constructed it to be parallel, and we did constructions in the first few lessons, and we can construct parallel lines. Now, we don't have to do a lot to do that. We just need to draw it and say, well, that's parallel. It doesn't really matter if you draw it perfectly or not. But this gives us two parallel lines and some lines that go through it. So we've got transversals. So it looks like we can use the properties that we've used before. So we're trying to set up the situation to be able to use our key items to unlock something else. So if I look at this, I'm like, okay, well, we'll write that down. JK, which we'll call this JK. That's one way to do it. And that, again, the book has used that. You can use whatever letters you want that aren't there, that you're not going to use. But we're just going to call it JK. And one of the reasons for it is that if I call this angle A, or the measure of angle BAC, it doesn't really matter. And I call this B. We like to use lowercase for our angles a lot of times. If I call that A, B, and C, those are the angles that I have in my triangle. But we also, by constructing that line, we have this angle and this angle, which I'm going to use. So we have D and E right there. And we're going to use all these, and it's going to be kind of cool. But we need to have the statement that says JK is parallel to BC. And we're going to say that we constructed it that way, or we've defined it that way, whatever works. And then something that we're trying to prove that the three angles of a triangle sum to be 180. So we can't use A plus B plus C is equal to 180, but we can use the fact that this is a set of these are consecutive angles on a line, and that adds up to be 180. That's always true. So D plus A plus E equals 180. Now we know that to be true because it is they're consecutive angles on a line. And that's one of the facts that we can use. So when we look at this, we're like, okay, well, we can use our other facts about transversals by, maybe we look at this line, and this line, and say that these we have our parallel lines and we highlight our transversal. We don't actually have to highlight it. That doesn't do anything for our proof. It's just nice for us to see. Well, using this, we can use alternate interior angles, because that's one of the facts that we can use to say E equals C. And that's because alternate interior angles. What else can we use? Well, if we get rid of that and we instead highlight this one, I'll wait till it straightens up one of these days. Something like that. Well, that's the other transversal, and we can say that D is equal to B because of the same reason. Because we only have four things or so that we can use. Four things and obvious axioms that we can use, so we got to use it. So D equals B for the same reason. Now, normally you won't write diddle marks. You'll fill in the blank, or you'll write out alternate interior angles, either way. But now what we can do is the reason we did that, the reason we set that up is because we're trying to prove A plus B plus C is equal to 180, but we've only got A in this equation that says it's equal to 180. We need to replace D and E. That's why we've related it to B and C. So I'm going to replace D with B because of substitution. So instead of writing D in this equation right here, I'm going to write B. My A is going to stay the same. And then instead of writing this E right here, I'm going to write C because E is equal to C. And I'm just writing the rest of the equation, and I'm replacing whatever I need to get where I need to go. But I have to have these statements written and the fact and the reason why I'm using them. Otherwise, I'm just randomly substituting stuff in. If you did that to a teacher would have no idea what you're doing, and you'd end up getting a 0. But if you had explained yourself beforehand, you'd probably get an A. It's that same idea. And this is because of the substitution property of equality. So reviewing what we have, we know that vertical angles are equal in measure. We know that transversal intersects a pair of lines. The pair of lines is parallel if and only if alternate interior angles are equal in measure and corresponding angles are equal in measure. If a transversal will cut through two lines in general, but if the lines it cuts through are parallel, the only way that can happen is if the alternate interior angles are equal and if the corresponding angles are equal in measure. So interior angles on the same side of the transversal add up to be 180. So again, the interior angles, remember the interior angles would be these two angles. Exterior would be the ones on the outside on the same side. So those are same side interior angles. The sum of the degree measures 180, and we proved that a little bit. So when we look at these things, I do love this thing. Check that out. You might have to type it, or you can just look in your lesson, especially the digital version on Great Minds, or just by getting the digital version off of Eureka's website. But right there, check that out. It's really cool. I love the history of some of these things. And I think I'll pause the video and start another one in a sec. Well, actually, we don't have that much left. Let's see. We just have this one. Construct a proof designed to demonstrate the following. If two lines are perpendicular to the same line, they are parallel to one another. Well, let's see. Let's draw two lines. And even if we don't draw it perfectly, one thing that we can do, once it straightens out, we can just draw two lines that look parallel, and then we're just going to say it is defined to be parallel. That's what's nice about it, is that nobody's expecting you to draw lines like this perfectly. So, let's see, let's do A and B, C and D, because we need to be able to label these things, E and F. And let's see. Yeah, that should be good. So I might do it like this. But either way, we have not proven that they're parallel yet, so we're going to have to use that. What other points do we need? We'll come up to more points as we go. So we have A, B, C, D, E, and F. So we're going to say that we know we have two lines that are perpendicular to a line. So we know that the line segment AB is, we use this symbol to represent perpendicular. It's kind of like the parallel symbol, but one of the lines is looks perpendicular. We know that is perpendicular to EF. They said that we have a line, it's perpendicular to another line, and we did our labels. So that's given. And we know that CD, the other line, is also perpendicular to EF, because all they said was we had two line segments or lines that are perpendicular to one line. So this one is one of the line segments perpendicular to EF, and the other one. And both of these are given, because that's the whole premise of our proof. And we need to prove that AB, this line, is parallel to that. Well, what's nice about this is that that's pretty easy to do. We know I probably need a point right here just to say, I want to be able to label these angles pretty well. You can either use a point right there and call it like G and H and say AGE, whatever. Or you can just, yeah, I think it's best to call it a point, because I'm gonna be dealing with a lot of angles here, and this will be easier. Let's deal with a point right here and just say that that's called G and that's called H. That's going to help us do our stuff a lot better, because I want to say that I want to deal with this angle right here. I know that I want to relate it somehow. So let's see. That's the measure of angle AGH. Well, that's equal to 90 degrees. That's because it's given right there. So that's equal to 90 degrees. But it's also, it's not just given. Sometimes we need to write it down. Perpendicular literally means, two perpendicular lines literally means that they're 90 degrees. So we'd write that down, perpendicular angles, perpendicular lines. So it'd be something like this. I'll write them both down. M of angle, because I've also got this one. M of angle CHF also equals 90 degrees. So both of these are for the same reason. They're perpendicular lines form 90-degree angles. So perpendicular lines form 90-degree angles. That is one of our axioms. That's the definition of lines being perpendicular. And so if these two are both 90 degrees and they're equal to each other, then we can replace them. Okay? So we can use the substitution property or the transitive property to, instead of writing those things, so we can write them as equal to each other. Because we didn't have something that actually said they were proven. I know it, like, you look at it and you're like, well, obviously they're both 90 degrees, so they're equal. You got to make a statement that says that. You know, sometimes explaining things to people, people lose track of the details. So the measure of this angle is equal to the measure of this angle because they're both 90 degrees, and we use substitution or the transitive property. Substitution or the transitive property. Now, what's cool about that is that we have these statements up here that say a transversal intersects a parallel line. So a pair of lines is parallel if and only if their alternate interior angles are equal in measure and their corresponding angles are equal in measure. And what's cool about that is that we just showed that we have this and this, which, if you notice, we have two lines and a transversal going between them. And we have shown that these two angles, these corresponding angles, are equal in measure, which means that they must be parallel because of the statement that we knew before. It says that we can use those. So if corresponding angles are equal in measure, the two lines are parallel. So we know that AB, and this is one of the harder parts. This is called a converse. And we'd want to put a lot of words right here, but the main thing is it's if two lines are cut by a transversal, and their corresponding angles are equal in measure, then they're parallel. And that might read differently from what you see over there up above. Because remember, this thing is saying a transversal intersects a pair of lines. A pair of lines is parallel if and only if their corresponding angles are equal in measure. or their alternate interior angles are equal in measure. Both of them will happen at the same time. But this one reads the opposite. It's the exact backward thing. But that's called a converse. Now let me show you this. Let me show you examples of the converse. So each of these three parallel line theorems has a converse or reversing. So basically we're just reversing the words. So let's look at the original real fast. If two parallel lines are cut by a transversal, then alternate interior angles are equal in measure. Now, if you were to look at this backward, if alternate interior angles are equal in measure with two lines that are cut by a transversal, then they are parallel. It's basically just reading it backward, but you have to logically make it make sense with the words. So let's look at what it says over here. I wasn't reading that. I was reading this backward. So the way they've worded it is, if two lines are cut by a transversal such that alternate interior angles are equal in measure, then the lines are parallel. So notice these mean the same thing. This one says it one way. If two parallel lines are cut by a transversal, then alternate interior angles are equal in measure. This other one reads the other way. It says if two lines are cut by a transversal, so we have not said anything about them being parallel. So if two lines are cut by a transversal, okay, such that the alternate angles are equal in measure, which is this part, then the lines are parallel. So it's the reverse idea, where we're going one way if two parallel lines are cut by a transversal. So we're starting off with that. Then their alternate interior angles are equal in measure. And this one is saying we just have two lines that are cut by a transversal. We don't know anything about if they're parallel. So we can look at the alternate interior angles, and if those are equal in measure, then it's parallel. It's kind of like a lot of our properties from before in algebra. So it's like we know that this property, a to the n to the m power, is equal to a to the n times m. So we might start off with this and turn it into that, or we might start off with this and be able to simplify it to be back to that, whatever is helpful for the moment. So if this is the statement that you're given and you know this statement is true, if you read it left to right, it's true. But that shouldn't change if you read it right to left. And we've had to use that property a few times in algebra. And that actually is the same idea as a converse. So if we have A equals B, writing it as B equals A is kind of like the converse. It's the symmetric property of equality. And basically, this is the word version. We go one way, that means that we must be able to go the other way. If we can prove that two lines are parallel, we can prove that their alternate angles are equal in measure. And if we can prove two lines are cut by a transversal and their alternate interior angles are equal in measure, then we can go the other way and prove that it's parallel. And the same thing here. If two parallel lines are cut by a transversal, then corresponding angles are equal in measure. And then reading the converse, if two lines are cut by a transversal such that their corresponding angles are equal in measure, then this proves that they're parallel. So this is just saying you know they're parallel, so their corresponding angles are equal. You don't know they're parallel, but you do know their corresponding angles are equal, then they must be parallel. So it's like reading it forward and backward. Let's look at this third one. If two parallel lines are cut by a transversal, then the interior angles on the same side of the transversal are 180. So these two angles would add up to be 180. Let's read it in reverse. If two lines are cut by a transversal such that their interior angles on the same side of the transversal add up to 180, then they are parallel. So we started with parallel, and we found out that these two angles add up to be 180. But if we don't know it's parallel, and we do see, and we can prove that these add up to 180, then we know that they must be parallel. So we're just going backward and forward with it. And we want to get good at that because we're going to have to use the converse a lot. So here's a good example of using something like that, a converse. In the figure to the right, x equals y. So we have corresponding angles. So we know that x is equal to y, which means that those two corresponding angles are equal in measure. But we don't know that AB and EF are parallel. We have to prove that. So we haven't been told that. What's nice about this is that we know that x equals y, because that was given. And we know that those are the corresponding angles. So we don't know if AB and EF are parallel. But since we know that we have two lines that are cut by a transversal and their corresponding angles are equal, we know that they must be parallel because of this property. That's the converse of our original statement from before. So AB is parallel to EF, and it's for the simple reason that where is it? The converse of what we already proved. So if we prove one thing, that means that same fact can be reversed to go backward. So again, this is a hard concept for students to get. That's why I'm going to repeat it a million times. We know that two parallel lines cut by a transversal, then we can use the fact that their corresponding angles are equal in measure. Okay? We just know that to be true. We have proven it a few times. But maybe we don't know the lines are parallel and we want to prove that they're parallel. If we know that the corresponding angles are equal in measure, they must be parallel for that same fact. It's just going the backward way of that same fact. So I'm not going to write it all down, but this is what you'd write down in that spot. Something around that and with enough information for us. All right. Now, again, if you feel a little confused about converse versus the original definition and going forward and backward with it, that's okay. This is one of the hard... I had a really hard time a long time ago understanding the original and converse. And sometimes it can kind of turn your brain to mush a little bit trying to think about it. Every time you try to reverse your thinking, it's kind of like one of those things like... you're trying to explain something to somebody. A lot of times something's true, but you don't know how to word it. A lot of times that's because you know the original statement. You don't know the idea of a converse. You don't know how to reverse it. You know something's true, but explaining it to someone doesn't make sense because you're having to reverse the whole idea. I mean, it doesn't make it less true. It's the same idea here. So if you feel like that's a difficult concept, join the ranks of everybody else. It's a hard concept to get, but once you get it, it's very easy. It's just you're going to have to take some practice kind of reading it and making yourself understand. Now, I'm going to try to provide some additional videos for that.